In the previous video, we defined the derivative to formalize the notion of an instantaneous slope. In this video, we will use the concept of the derivative to obtain an expression for the instantaneous slope of power law functions. Even though such functions seem simple, they can help us to analyze more complicated functions because many seemingly sophisticated functions can be broken up into sums of terms that individually are examples of power laws. Before deriving the general expression for power law functions, we will warm up by calculating the derivative for the specific, simple example of a quadratic function. In particular, this is the plot of a function whose association rule is f on x equals a times x squared. We want to calculate the derivative of the function using a succession of turquoise triangles with left-hand corner planted at x equals x naught. We will find that df dx evaluated at x equals x naught equals 2 times a times x naught. Substituting the association rule ax squared into the definition of the derivative gives df dx evaluated at x equals x naught equals the limit as delta x approaches 0 of numerator a times the square of the quantity x naught plus delta x minus a x naught squared divided by denominator delta x. Distributively multiplying or foiling the binomial turns the numerator into a x naught squared plus 2a x naught delta x plus a delta x squared minus a x naught squared. Cancel the plus and minus a x naught squared. df dx at x equals x naught is the limit as delta x approaches 0 of numerator 2a x naught delta x plus a delta x squared over denominator delta x. And this factor of delta x from the denominator is common to both terms in the numerator. Dividing this delta x out, we get the limit as delta x approaches 0 of 2ax naught plus a delta x. As delta x becomes arbitrarily small, the quantity 2ax naught plus a delta x becomes arbitrarily close to 2ax naught. Thus, the limit as delta x approaches 0 of 2ax naught plus a delta x is 2ax naught as expected. The instantaneous slope for this plot increases, or becomes more upwardly toward the right steep, as the foothold for calculating slopes, meaning x naught, moves farther and farther to the right of x equals 0. Now that we have warmed up by applying the definition of the derivative to the simple example of a quadratic function, we can derive a more general power rule. This is a plot for a generic power law, meaning a function with association rule f on x equals x raised to some power n. In this specific illustration, it looks as though the generic function drawn might be a cubic with n equals 3. For the purposes of our derivation, we regard n as a generic integer. We will use x equals x naught as a foothold for calculating the derivative of the function. The perhaps familiar result that we will find will be that df dx at x equals x naught equals n times x naught raised to the n minus 1 power. Substitute the association rule f on x equals x to the n into the definition of the derivative to get df dx at x equals x naught equals the limit as delta x approaches 0 of the fraction with numerator x naught plus delta x quantity taken to the nth power minus x naught to the n over the denominator delta x. Using the binomial theorem, the term x naught plus delta x quantity taken to the nth power can be written out as the sum from k equals 0 to n of n factorial over n minus k factorial times x naught to the n minus k power times the kth power of delta x. We write out the first two terms in the sum explicitly. For k equals 0, the corresponding term in the sum is n factorial over n minus 0 factorial times x naught to the n times 0 powers of delta x. For k equals 1, the term is n factorial over n minus 1 factorial times x naught to the n minus 1 times 1 power of delta x. The remaining terms for k equals 2, 3, 4, and so on, as necessary to reach n, remain collected succinctly in the sum from k equals 2 to n of n factorial over n minus k factorial times x naught to the n minus k times the kth power of delta x. Cancel the first and the last terms, which are plus and minus x naught to the n. To complete this step, recall that 0 factorial equals 1. Divide all remaining terms in the numerator by the common factor of delta x in the denominator. This means that the kth power of delta x in this red marker loop becomes the k minus first power of delta x in the next line. Because this sum starts from k equals 2 and the power of delta x is k minus 1, the powers of delta x that will appear, of course with additional coefficients, are delta x, the square of delta x, the cube of delta x, and so on as necessary to reach the n minus first power of delta x. As delta x approaches 0, the sum of n factorial over n minus 1 factorial times x naught to the n minus 1 plus all of these terms with ascending powers of delta x, this sum becomes arbitrarily close to simply n factorial over n minus 1 factorial times x naught to the n minus 1, which itself can be written out using the definition of a factorial in terms of factors descending in the numerator from n and in the denominator descending from n minus 1 and from 1. Cancel the many factors that are common to n factorial and n minus 1 factorial. The only surviving factors are n and x naught to the n minus 1, as expected. While we have derived the derivative of a power law using the version of the binomial expansion valid for powers of n that are integers, the same rule applies to non-integer n. Viewers wishing to follow up on this point might be entertained by looking up a version of the binomial expansion useful for non-integer powers. For both integer and non-integer powers, we memorize the rule using one same mnemonic. We recite, bring down the power n and subtract 1 from it upstairs. Now that we have derived the power rule, we will keep it in mind rather than rederiving it for each use. In the following video, we continue to expand our crib sheet by studying the chain rule, which is used when calculating the rates of change of composite functions.